start our talk now. Today we are doing our GeoSeminars talk. This is the 5th talk in our series. And on the left, you can see our flyer for the rest of the upcoming talks every 2 weeks. And for today's talk, and we are very happy to have Alejandra Ortiz speaking about understanding atoll island evolution through remote sensing and modeling. Do you want to give the next slide, Kirsty? So just to introduce our speaker, Alejandra Ortiz grew up in Miami, Florida, and has spent most of her life within a couple of miles of the coast. She majored in geosciences and classical civilizations at Wellesley College, while completing a senior thesis focused on understanding the wave climate around Vieques, Puerto Rico. She earned a master's in civil and environmental engineering at MIT's joint program with Woods Hole Oceanographic Institute, WHOI, in 2012, researching the role of plants in changing sand deposition patterns in rivers. She completed her PhD in marine geology from the MIT WHOI joint program in 2015, with research on understanding the evolution and formation of coastlines from barrier islands to atolls. Prior to starting a faculty position at North Carolina State University, Dr. Ortiz completed a postdoc investigating the role of wind and waves on driving land loss on Mississippi Delta marshes. She worked for 3 years as a professor in the Department of Civil Construction and Environmental Engineering at NCSU before moving to Colby College's Geology Department in 2019. Her original training was in marine geology, but she has also worked in coastal engineering and mostly does coastal geomorphology, which is the study of landscape evolution. Dr. Ortiz's focus on understanding the impact of climate change, focuses on understanding the impact of climate change, and in particular, sea level rise on coastal landscapes over decade to millennial timescales using numerical computer models, remote sensing, and fieldwork. She has worked in lots of different environments, from barrier islands to marshy deltas to tropical atolls. Recently, she is dabbling in deep neural networks as a method for automated land cover classification of atolls from satellite imagery. Ortiz teaches at Colby College a range of undergraduate courses from geomorphology to the water planet. I also forgot to mention in the beginning that anybody who would like to ask clarifying questions, either on the Facebook or on the GeoLatinas Zoom call, can chime in the chat, and I will bring it up to the speaker. Otherwise, we will also have questions taken at the end of the talk. So without further ado, Dr. Alejandra Ortiz, take it away.
Okay, I think the screen sharing should be working now. Thank you so much for that introduction. I really appreciate it, and I'm very happy and excited to be here today to be able to give a talk on some of the work I've been doing. That was a very detailed bio, so I will kind of skip past a couple of things. But a lot of the big picture that I'm interested in is kind of trying to understand the drivers of coastal change. And in particular, when we think about atoll islands, considering ideas of resiliency and what's going to happen to these locations in the coming century. And the work I'm talking about today is really the compilation of work from a lot of different students that I've had the great pleasure of being able to interact with over the past 5-7 years now. So at Colby College, I've worked with Manny Salas, Bentley Myers, John Connors, Vanessa Lasta, and Eric Trickasemsak. And then at North Carolina State, a lot of the work that you'll see today is a product of Faith Johnson's master's work, as well as Carter Rucker, Jonathan Woodruff, and Melody Thomas. Oh, and also Sean Daly helped create the database I'll talk about. A lot of my work is driven by understanding atoll resiliency and trying to investigate some of the primary drivers of kind of the land change on these little islands and what might be controlling that. For example, is it things like external controls such as wave climate, storms, or is it more driven by internal sediment production, or how happy the corals are, things like that. And so to do this, we've created a global atoll database, very inclusive one, And we're working on quantifying relationship between wave climate and atoll morphometrics, otherwise known as their size and shape. So I'll go a little bit into my background, but that's been pretty well covered. And I'll talk about the atoll database, some modeling work I've done looking at the formation of the atoll islands, which I also call MOTU, and then some more recent work where we're trying to measure kind of global scales of MOTU morphometrics, and then some of the relationships with the offshore wave climate. So as was already stated, I grew up in Miami, Florida, but have spent now a decent amount of time in the New England area. I love cross-country skiing and hiking. I have a dog and a cat and live in a tiny house. And here is a mock-up of a Pokemon card that I have my intro students make their own version of to get to, so I can get to know them a bit better. But yeah, previous work, as was stated, I've done work looking at sediment transport and vegetation using a laboratory flume to kind of simulate that, as well as a lot of modeling work trying to predict shoreface evolution on barrier islands, and then using remote sensing to look at changes on the Mississippi Delta and some of the potential drivers of land loss on that system. More recently, I've been lucky enough to work with some great colleagues at North Carolina State, and we've been investigating a range of things like how does marine renewable energy devices impact ocean morphology? What are some ways we can think about bridge scour, kind of the erosion around bridge piers, and maybe some mitigation options? So when I think about coastal geology, one of the key things for me is centering it within the idea that over the past, 20,000 years, we've had significant changes in global sea level, over 100 meters of eustatic sea level rise. But over the last 6,000 years, we've had very, very low rates of sea level rise, less than a meter per 1,000 years. And so when we think about the coastlines that we see today, they have evolved to these relatively low rates of sea level rise, which, as we all know, is not what we're facing currently and what we're going to be facing over the rest of the century. So this is a graph looking at projected rates of eustatic sea level rise out to only 2100, forecasting different scenarios. And a common thing is that we're going to see at least a half meter, but more likely a meter of sea level rise globally by the end of the century. So we've had a significant shift in how fast things are changing for coastlines. And so, of course, that starts to then ask the question, well, what's going to happen to these coastlines if we're suddenly making it really fast sea level rise, in addition to changing storms and waves and ocean acidification, kind of all these other risk factors. And so one area I've really liked to work in is atolls or atolls, and about half the people like one pronunciation versus the other. I try and use both. But of course, we're going to define it. I'm going to have it a very broad definition. So the way that I'm defining it is that there is some kind of coral reef platform, and it's encircling or kind of surrounding a central lagoon. And on top of that reef platform, we may have land. And I'm going to call those land masses, those little islets, MOTU. This is a Polynesian term. And you'll hear other people use terms like reef islets or cays, or atoll islands. They all have somewhat varying nuances, but I tend to use the word MOTU throughout. Key aspects about these landforms is that they're very low elevation, and they're where everyone lives. So here in the bottom right, we have kind of a cross section showing the deep offshore ocean that shallows up to this reef flat. And then over here on the left is that lagoon that it's supposed to be surrounding. And on that reef flat, we can have these little islands. And, it's typically going to be made up of gravel and sand, very carbonate heavy, and kind of tends to be produced locally. So there's two interesting parts. Well, there's a lot of interesting parts, but there's two things when we think about kind of atoll formation and MOTU formation. And one is that atoll formation is something that Darwin, the biologist, actually came up with, kind of the theory of how atolls form, which is that we have this volcanic island, right? And As it becomes subaerial, we'll get the growth and formation of coral reef on the outer edges if it's in a tropical warm ocean. And then over time, that volcanic island may actually sink because there's no new lava being produced. But the coral reef will continue to kind of keep pace with where the current sea level is. And then you get the formation of this really kind of large coral platform. And on top of that, that's where we might find these motus. And so you can see there's a little animation showing this in the upper right, as well as some cross sections and kind of top-down views of how that might work. Darwin actually got a lot of this right. The thing he didn't realize was sea level changes. So he didn't kind of account for that. But, you know, we as geologists and earth scientists know the fact that over the last, millennia of Earth's we've had significant changes in sea level. And so that's one of the other factors that can drive the formation of that kind of reef platform and whether or not it's able to kind of keep up with changes in sea level so that we might get an atoll as shown here, or if we then instead just get kind of a submerged seamount. The key aspect is that the atolls are forming over these really long timescales, like hundreds of thousands of years, versus the islands on the reef platform, the motu, form much more quickly. So what we started with in my lab was Sean Daly helped me create a very inclusive atoll database. And based on a very broad thing that we've got a coral reef platform, it's encircling a central lagoon. There may or may not be land on top of it. And there may or may not be a central island. Like, in other words, the volcanic central core might still be subaerial. What we have here is a map of what he's found, and the dots are colored by the country. And so as we can see, there's a very large proliferation of atolls in the Pacific, and then we also have a pretty large amount in the Indian Ocean and a much smaller amount in the Atlantic Ocean. And we kind of started using that as a starting point to do some of the further analysis. So the fun thing about these locations is they are completely different than most places on Earth. I grew up, as I said, in Miami, Florida. I was very lucky to be able to travel to the Caribbean, but up until my PhD, I never actually went to an atoll. And they had these distinct geomorphic regions in some ways. So you have that kind of inner lagoon surrounded by the reef flat, and then out on the ocean, it tends to get very deep very quickly, and then it will shallow up to this reef flat of about 1 meter depth. So what we can see here in this image on the upper left is we have all the waves breaking on the outer edge, and you can see behind that the ocean is a much darker blue. And so that's kind of the deep ocean. Then where the edge of that reef flat is, the waves break because it gets so shallow. And then on the reef flat itself, we have this very flat, shallow, relatively low energy environment. And here in the middle is a picture if I took my camera and kind of put it in the water of the reef flat. So we can see a small little coral growing. But for the most part, the reef flat itself is not got active growth. And most of the active coral growth is on this outer edge where the waves are breaking or within the lagoon. If I also then stood in the reef flat and kind of looked straight down with my camera, here's a little image of some of the sediment that might be moving around in this environment. And you can see that's really clear pieces of coral. And when we look at the beaches of a motu, we commonly can get this thing of a very large gravel ridge, as shown here. And if we look at a trench, we can have huge variation in grain sizes. So, we've got boulder-sized pieces of carbonate reef flat down to very fine grained sand, all shown in this trench. So the work we've been doing in my lab is trying to kind of think about atoll survival by 3 different ways: some field work, some modeling, and some remote sensing. And I'm going to start with talking a little bit more about the modeling. Oops, sorry. And in some ways, the underpinning is trying to reduce the atoll itself to the most basic pieces. So what we've done when I think about atolls is I think, okay, there's a lot of really deep water around on the outer edge. That's this dark blue. And then inside, we've got kind of the shallower lagoon. And then that's surrounded by this reef flat. And on the reef flat, we have these little islands that are called reef islets or motus. And so at its basic piece, there's kind of 3 parts to these environments: water, reef flat, and land. And so I started during my PhD with looking at, well, how do those motus form, right? Like, what is the mechanism that drives the creation of these? Because we know from aerial images and satellite images that these things can form on timescales of decades to centuries. So they can kind of come and go pretty quickly. And the other key piece is this is where people actually live. And so these are two images of atolls in French Polynesia. On the left, we have Rangiroa, and on the right, we have Hikueru. And what we find, and this is a common behavior, especially in French Polynesia, is that if we look on the northern side of the island, right, we have this kind of long continuous motus. And so you can see a zoom in down here on the lower left, and it's kind of this connected island that's quite long, kilometers in length, but not very wide. On the other hand, if we look on the southern part of both of these atolls, we have either no visible land, no motus, or we have what's shown here in the bottom right, these much, much smaller little motus that have much greater variability in their width and length. And so the question starts to become, well, why is that? Like, why do we have parts of this reef flat where we've got land that's developed and other parts where land doesn't develop or it looks really different? And, people have been trying to kind of figure this out using a range of techniques. And so that's been a big driving question for my work, is trying to figure out, well, what processes are affecting the development and evolution? How important are kind of big storms, cyclones and hurricanes? And then, well, if we understand that, can we understand the impact of sea level rise on these in the future? So to get at this, I started with using some numerical modeling with XBeach. So XBeach is a morphodynamic, hydrodynamic, open source model, aka it's going to tell us what the waves are doing and how that can drive sediment, which long-term can tell us how the land's going to be changing. And I'm giving you the cart before the horse. I'm giving you the answer from this work, which is we came up with kind of a conceptual model to explain the formation of motus on these reef flats, where initially, if we have this underlying reef platform, we would expect it to grow to an equilibrium depth based on the offshore wave climate. And over time, it'll widen to an equilibrium width. Once that reef flat can get wide enough, what we actually can start to happen is have deposition of sediment in the middle of that reef flat. And if you put enough down, you can actually start to create a motu, a landmass. And over time, the prediction is that the motu is going to continue to prograde oceanward, as shown in this bottom left, till it reaches a critical reef flat width. And so that's something we're going to come back to a lot in this talk. Back to XBeach. I ran it in 2D mode, so kind of cross section. I could vary how deep the reef flat was. So that's that HR value shown in purple. I could vary how wide my reef flat was. I could vary whether or not I had a motu, and then I could vary the offshore wave height and wave period. And because it was a relatively simple model, I could run a lot of these simulations with a lot of variations pretty quickly. And so here is hopefully a movie that'll play, showing the simulation of offshore wave height in blue. And then as that wave approaches the reef flat, which is shown by that black line, what happens. And so we can see here, we're kind of forcing it with this like 2 to 3 meter offshore wave. And as we get on shore, the waves shoal and break, and then not much wave height as you get onto the reef flat, which is very common. The green line is showing our bed shear stress. Okay, so this is the key driver of sediment transport. And what we can see is that we get these big peaks in bed shear stress right near the edge of the reef flat where the waves are breaking, and then it tends to decay over the reef flat. So I would run these simulations, for a couple hours till we'd reach hydrodynamic equilibrium. So there wasn't really any changes in the hydrodynamics. And then I could average over the length of that simulation, what was the mean offshore wave height or other factor, other variable. And so what's shown here is for 3 different reef flat depths, ranging from 1 meter to 5 meters, what is the bottom shear stress, the average bottom shear stress that we measure. And what we find is that as we increase the water depth over the reef flat, we actually decrease the bed shear stress. And the dashed lines are showing the minimum bed shear stress needed to mobilize sand, coarse-sized carbonate sand, or to mobilize a coarse boulder, carbonate boulder, excuse me. And so what we find is that as the reef flat is deepening, we are getting lower and lower bed shear stresses. So we actually get to a point where we no longer are moving sediment over that reef flat, which would allow the reef flat to have sediment deposit on it and shallow up over time till it reaches kind of this critical or equilibrium depth with whatever the offshore wave height is. We can then also kind of do the same experiment with saying, well, what happens if we start with a very narrow reef flat versus a very wide? And what we find is as the reef flat widens, our bed shear stress again drops. And so that's shown by these three things. And for very narrow reef flats, we're able to mobilize all sizes of sediment. And basically, if there's any sediment that's produced here at the edge of the reef flat, it would be moved into the lagoon, which would allow our reef flat to kind of get wider and wider as it progrades into the lagoon. So over time, there we go. Sorry, that's being a little slow. Over time, what will happen is you can kind of continue to increase this width of the reef flat, and suddenly what will happen is that your bed shear stress will actually drop below the bed shear stress needed to mobilize sand, at which point you could start to deposit sediment on that reef flat. And once you've deposited sediment and make it really, really shallow, you actually would continue to deposit. You would create a positive feedback that would create a proto-motu or kind of an initial island. So then with the numerical modeling, we tested, well, what happens if we have a motu versus no motu present? And so once we have a motu, we see this purple line, and we have a significant change in the bed shear stress. And what we find is that the bed shear stress now is much closer to 0, but we also get more offshore directed bed shear stress. So a negative value of bed shear stress just means that sediment would move towards the ocean and not towards the motu. And so down here in the lower right, we're showing for varying reef flat depths, what is the predicted bed shear stress. And again, we can play with how deep is that reef flat and how wide is it when you have a motu. And what we find is that depending on the offshore wave height, we have this change in behavior of when we expect to have sediment moving onshore towards the motu or offshore towards the ocean, okay? And there becomes this kind of critical width and depth of the reef flat that we expect kind of the system to move towards based on the predicted sediment transport. So all that being said, this very simple 1D model seems to be a way that the system would self-regulate to create, you know, these long motus that reach a near critical width of the reef flat. And so this is going back to that image of Rangiroa on the northeastern side, and we have this long motu, and we can see that the width of this reef flat seems to be pretty consistent. And we find this visually on kind of a qualitative level throughout French Polynesia. And so the question then started to become, well, all right, my 1D model predicts a certain type of behavior that I expect to have about a 200-meter reef flat in front of these long motus. And based on some Google Earth searches, it seems like I'm seeing that, but is that actually being found globally? So from this initial work, the key aspects were that the direction and magnitude of the bed shear stress is going to be strongly influenced by how deep your reef flat is, how wide it is, and what your offshore wave conditions are. And then over time, we expect the system to self-regulate to this equilibrium water depth and width of the reef flat. And any changes in our offshore wave climate or in, say, sea level would also drive then changes in what would happen kind of to the movement of sediment. So given this, our next piece was, okay, can we start to look more consistently at what the morphometrics are? What are the size and shapes of these reflats and motus globally? And so what we've done is we created this atoll database. It's got about 623 atolls. And again, it's a very broad definition. Most people would say that there's more about 450. But we wanted to be inclusive, and then we figured we could always cut down and, you know, make subset it more easily. What we've done, and in particular what Faith Johnson has done, is we have calculated morphometrics for 1,753 motus, so little islands, 596 reflats on 154 atolls. And so what these pink dots represent is the locations where we have calculate these morphometrics. The X's are all the locations we've identified as a possible atoll, and then the blue are ones where we've created some satellite composites or satellite images of the atolls, but we haven't calculated the morphometrics yet. And so this is work primarily driven by Faith Johnson, who's previous master's student, as well as Manny Salas and Bentley Myers. And the kind of general outline is that we create these composites, we identify the objects, so the motus or the reflats, and then we calculate the morphometrics. And then we want to compare that to the offshore wave climate, because that's ultimately what my model was saying should predict kind of those widths in front of the motus. So to give you a sense, here is an atoll in French Polynesia. And what we've done is we will separate it into these kind of four cardinal quadrants: north, east, south, and west. We can calculate all of these values of, say, motu width, motu to reflat width, reflat width, and kind of this effective reflat width. And we can do it on a per point basis. So this is for every single pixel in our image, we've calculated these values, but then we can also, of course, average at the atoll scale or at the like motu scale, or average by kind of these cardinal directions. So to create the composites, one of the key things is that when we have these satellite images, they're great, but clouds tend to be an issue. So what we've done is we create what's called a temporal composite. So we take every image over, say, a 3-year period that Landsat has of Bikini Atoll, as shown here. And we average per pixel per band after removing the clouds. And so what we can then create is something that's cloud-free and tends to have a lot fewer issues with georeferencing and other things that might kind of interfere with our automated classification. And so the general step is shown here. For Katui, we create a temporal composite. We then currently classify that image into reflat, which is shown in red, water, which is shown in blue, and land, which is shown in yellow in this image. And so we use k-means classification. It's an automated method. And then from that, we can then identify each of those objects and kind of outline the motus in green and the reflats in blue. And you can see here, we're actually able to resolve this small channel that's shown in the reflat on the Google Earth image versus the Landsat image. And key aspects to remember that Landsat has only 30-meter resolution, so it's not going to be as high resolution as we would see in, say, Google Earth, but it's free, which is why we're using it. We've also had Landsat since the 1980s, which is really helpful. Okay, so we calculated these morphometrics for about 60 different atolls in French Polynesia, and we can start to bin them, as I said, by kind of that north, east, south, and west quadrants. And we start to find some very consistent patterns. First off, the effective reflat width, so how wide that reflat is in front of the motus, is much lower on the north and east side of all of our motus in French Polynesia than on the south and west side. And the motus are correspondingly much larger, so they're kind of longer, as shown here, on the north and east side. And as a result, they're blocking a significant portion of that reflat. In other words, we don't necessarily have movement of stuff around the motus as much into the lagoon because they're much longer. Versus on the south and west side, we have these much shorter motus and wider reflat widths with a much larger standard deviation. And so what I've plotted here is MO2 length versus that reef flat width. Okay, so how wide is the reef flat in front of the MO2? So it's kind of these two things, and here's that schematic. And I've colored the dots by north and east as kind of this blue and darker green, and then south and west. And what we see is that for these longer MO2s, we get a near constant reef flat width in front of the MO2s. And so this is, kind of what we were predicting would happen based on our qualitative analysis in Google Earth, that on these longer MO2s, we're getting these much more kind of consistent, about 20% of the total reef flat width is open in front of the MO2s. So here it's the same graph. I've just normalized the ocean reef width, so this distance, by the total reef flat width. And it's really interesting because for really small MO2s, like these ones shown up here, we have huge variation in how wide that reef flat is in front of it. But once we get these bigger ones, they seem to get much more consistent to about this kind of 180 meters in front of it. And so what we can do is look at this subset of data. So for atolls, or for MO2s that are longer than 5 kilometers, we can plot that reef flat MO2 width compared to the offshore wave height for storms. And there seems to be this trend, and this is very preliminary data, where as we have increasing wave height, we see a bit wider reef flats in front of the MO2s. And so this seems to pair with some of the predictions we had from the X-Beach modeling. And to give you a sense, right, I mentioned that we had done this on 154 atolls. So all of those pink dots in the image, we've calculated these morphometrics. And we segregated it into kind of 3 bins. One, what we're calling equatorial atolls. And so these are within about 5 degrees of the equator. Then we have the mid-latitude or mid-tropical atolls, which are between 4.7 degrees and 14 degrees, which is kind of this shade area. And then our high tropical atolls, which are so far we only have numbers in the South Pacific right here and are pretty dominated by French Polynesia. But we can calculate, again, the average MO2 area, the average reef flat width, the total reef flat width for all of these different atolls. And we can start to look at how these values might change with the different binning. And so here is just kind of these distributions of ocean reef width, okay? And so that is this value right here, which is shown in purple, versus the MO2 width, how wide are the MO2s, how wide are the reef flats, this blue line. And we can start to pull out, if we look at just say that total reef flat width, we can look and see how that can vary based on where the atoll is. So how close is it to the equator? We see some different behavior, and same for the MO2s. For example, the MO2s that are closest to the equator, what we're calling these equatorial atolls, have a very wide distribution of how wide the MO2s are. Okay, so you kind of get fatter MO2s near the equator. And the further away we are from the equator, the more the MO2 width is consistent and smaller. The mean and the standard deviation is less. And similarly, when we look at this value of the MO2 reef flat width, as we get further away from the equator, it gets smaller and smaller. So this is a same graph as I was showing before for just French Polynesia, but now looking at all of our atolls on a per MO2 basis. And so the dots are colored where the MO2s near the equator are blue, the mid-tropical are orange, and the high tropical are green. And we have this similar pattern, which is that once MO2s are long enough, we get a very consistent width in front of the reef flat. But for the smaller MO2s, we have large variation in how wide that reef flat is. We can then normalize this plot. That's all that's shown here. It's the same data. We've just normalized the length of the MO2 by the total length of the reef flat, and the width in front of the MO2 by the total reef flat width. And again, we have this consistent behavior that about 20 to 22% of the reef flat is open in front of these large motus. So to kind of test our automated classification measurements, we compared our measurements of total land area, reef flat area, and lagoon area to measurements that we have found reported by others. So that's what our y-axes are. And we can see that we actually are under predicting the total land area on average by about 3 kilometers squared. Over predicting it by about 3 kilometers squared, but we're under predicting our reef flat by a decent amount, 26 kilometers squared. And we're quite good at predicting our lagoon area. So this is an area where we're clearly still trying to get a better handle on how well our methods are for classifying these landscapes and then calculating the morphometrics on it. And we know that we have bias because we're using Landsat, so we only have 30-meter resolution. And we're trying to avoid hand digitization, which is what people have tended to do because it's slow and, I'm lazy. So coming back to this image of Rangiroa, this is really kind of what motivated it, is this idea that on the north and eastern side of this atoll, we have lots of land. It tends to be connected. It tends to have a very thin reef flat width in front of those. But on our south and kind of western sides of this atoll, we have large areas where there's no motus and no land. And then we have other areas where we have these much smaller motus that have a wide variety of shapes and then kind of how far back they are from the reef flat. And so what I've kind of come up with is a conceptual model of what might be happening once we create these motus. And that this idea is based on the hydrodynamics, we expect that once the reef flat is wide enough, we can start to create a motu. But over time, some of those motus seem to merge and become these really long motus that then have a very narrow reef flat width in front of them. But others stay quite small and variable. And what we think is happening is that in some areas, we have a significant amount of flow around those smaller motus, allowing for sediment to be routed around them. And so thus you can kind of continue to potentially widen your reef flat and not join these motus. Versus in other ones, these kind of channels between the motus close. And so then we get these merges and a much longer motu, which would then start to prograde towards the ocean like our model predicts. And so these are kind of the formation of what we're seeing on the north and eastern sides of French Polynesia versus what we're seeing on the south and western sides. So I know I just went through a lot rather quickly, but I was trying to be mindful of time. At this point, we've done this for, as I said, 154 atolls. But we want to expand that to, about the 400 atolls that most people agree are considered atolls. We also want to look at what are some of the changes to these morphometrics over time. We have Landsat imagery, as I said, back to the 80s, and in, on these islands, coverage probably back to about 2000s. And then we want to compare it to the offshore wave climate. And then hopefully this summer, I'm going to get to go to this particular atoll in Belize, Glover's Reef, and stay right here at the Marine Research Station with a couple of students, but COVID willing. So these are references, and then, acknowledgements. Again, this couldn't have been done without the help of all of these students. And this is also work I did with my PhD advisor, Andrew Ashton, and I've had funding from Colby College and North Carolina State University. Thank you, and I will take questions now.
Thank you so much for a great talk. I guess those on this call can put clappy hands for our speaker. And if anybody has any questions in the Facebook Live, you can leave them. I just want to amplify what Clara said on the Facebook. She said, what a great presentation and research. She made it easy and fun to understand for those of us who are not familiar with the topic. For those who are following on Facebook who didn't quite watch the whole thing, you can, I recommend that, or she recommends that you watch the full webinar, especially if you weren't able to connect from the beginning due to our connection issues. And thank you so much for sharing your research with GeoLatinas and the GeoSeminars. Anyone who's still with us on the Facebook Live, if you have any questions, or if you want to thank the speaker, you can do so, and I'll amplify that as well.
Thank you. I'm also happy to answer questions via email as well if you don't want to ask right now. It's not a problem.
Oh, that would be great. What is your email, just for those watching that they
acortiz@colby.edu. So I'll type it in the chat.
Yeah, I'll pass it along to the Facebook comments. All right. Let me just type that in. Okay. As we wait to see if anyone else has any questions, I have a couple as well. So I'm quite a bit new to the geosciences in general, so I don't know much about like atolls and motus and everything. I was wondering if the development of atolls and motus are different depending on the location that they're in, because I think you mentioned a couple of different regions, especially on that map where you were kind of like pointing out all the locations. If you, I don't know if you want to go back to that slide to talk about what differences there are between the different locations of where the atolls are.
So it's a great question. And I skipped over a lot of work that's been done already. Mm-hmm. But one of the things is separating the difference between the formation of the atoll and then the motu. Okay. So there's been some really interesting modeling and kind of field work done by a colleague of mine, Michael Toomey, along with Taylor Perrone and Andrew Ashton, and several others, looking at how the atoll forms and why we might have the formation of like a seamount sometimes versus an atoll. And what they found is that it kind of requires some really particular conditions and changes to sea level and locations within kind of how warm the ocean is, right? Because it's very dependent on how happy the corals are, basically. So that's one that's driving kind of this long-term, again, tens of thousands, hundreds of thousands, even millions of years formation. But once you have an atoll, whether or not the motus are forming and how they're forming definitely does vary. And so previous work has come up with a number of different theories that the formation of these little islands are dependent on the presence of hurricanes, as well as just kind of changes in wave climate, as well as how much sediment is being produced. And so part of what we were trying to do here with this remote sensing is start to actually quantify these numbers, right? Because if we can get this like baseline information of, okay, how big are the motus? How many are there? You know, how wide are they? Then we can start to think about, well, what might drive those differences? And so, you know, here we did a very basic binning of saying, okay, everything that's kind of close to the equator, we're going to lump, and then everything that's a bit further versus as far away from the equator as you get, but still kind of be within the tropics of Cancer and Capricorn, you know, do we see differences? And the answer is yes, right? So like looking here, I've got mean motu lengths. And so I can see that the atolls in the kind of the high tropical, so kind of far away, and in particular, this is French Polynesia, have much longer motus on average than the ones that are close to the equator. But if we look at some other metrics, we can see that the motus closer to the equator tend to be much wider. So they're kind of fatter, but not as long. And the other interesting thing, though, is that we had this behavior of wider reef flats closer to the equator. So when we look at this graph, we can actually see this where the equatorial ones are these blue dots. And so we actually see kind of this larger reef flat width in front of the motus for the long ones. But when we normalize by the total length of the reef flat, and when we normalize by how wide the reef flat is, they actually are all still kind of collapsing to about this 22%. So I thought that was actually really interesting. And, you know, one of the key things we're trying to do with this is creating this like open source database, because there's a ton of data here and we've just started to analyze it. So I think there's a lot that people can use. And thank you, Clara, for recognizing, you know, the contributions. The reality is this work, you know, this is stuff that I started in like 2014. And so there have been so many people who've worked on this, and I can't do it all, not even close. So I've been really lucky with having great students.
Just to let those on Facebook Live know what Dr. Ortiz is referring to, Clara put in our chat on this Zoom call that she was really happy that our speaker acknowledged all the people who have been working on with her, as well as just in general in this kind of research, and that recognizing contributions is so important and keeps people motivated. I actually noticed the same thing, especially I really like talks where people start off talking about those who have worked with them, as well as students especially.
Yeah, the science is not done in isolation, and it's not done without great people collaborating and kind of a lot of work from different people. So
of course,
I've been very lucky.
Someone in the Facebook just wanted to ask where the talk is being recorded and if the recordings are being stored. I believe you can go back and watch this Facebook Live. Facebook, I think, posts the recordings of all the past live episodes, and we will also be posting on the GeoLatinas YouTube for the actual like Zoom recording of this conversation that we're having now. Let's see. Yeah, so we'll upload that in a little bit. Christy, do you want to just like go to the slides where we have that information of the YouTube channel and things like that? Yeah, we have some slides just to mention that. Before we get to that, we do want to show our certificate to our speaker to thank her for doing this talk as well. We give this certificate to all our speakers just to give a little thank you for contributing to our education and outreach initiative and for our GeoSeminars talks in general.
Thank you very much. You know, I'm just so amazed and impressed by GeoLatinas, and oh, I love living in Northern Maine, but the thing I do miss is being able to speak Spanish more. Though, of course, if I tried to give this talk in Spanish, it would be terrible. So I appreciate that you let me speak in English, but thank you.
Christy, do you want to change to the slide? Yeah, with the information about, yeah, that's great. Yeah, so we do have recordings of our talks on our YouTube channel. I believe we have both the series that we do in Spanish, as well as this one. This series is in the English portions, and we have different speakers for the people who contribute to the Spanish seminars, as well as these English ones. And we also have our thesis initiative, where speakers will present work that they did for their thesis. And you can also follow GeoLatinas on our social media channels. Again, there's our YouTube at the top, and we also have Facebook, Twitter, and Instagram, and apparently LinkedIn, which I didn't know about. Anybody else who wants to ask any questions in the Facebook or leave any comments? I'm just going to respond to Isamar's comment about the recordings in text in case she's not listening to the recording at this time.
Isamar made another question about the presentation.
Oh, she gave another question. Okay. Can you read it, Christy? I just want to respond to make sure that she knows about the recording situation.
Okay, yes, perfect. She says, also you mentioned using Landsat time series data with future analysis, do you think you will use higher resolution imagery, or will it be better to stick with the 30-meter resolution for a consistent and serious record?
So great questions, Isamad, and not surprising that you would be asking, given all the cool work you do with remote sensing. So there's kind of two huge benefits to Landsat for me. One is the fact that it's free, and two is the fact that it did start in the 1980s. So in terms of kind of the time series analysis and temporal change, if I'm thinking about long-term decadal change, Landsat is what I'm turning to. However, one of the things we're trying to do in my group is look at the spatial bias we have by using Landsat, because it is only 30-meter resolution. So we're working on using Planet Labs PlanetScope imagery, which we're on average seeing kind of 3-meter down to 1-meter resolution. The big issue with that is it's not free. You can get some subset of it free per month, and so we do that, but it limits significantly kind of how much data we can look at easily. And it was only, most of the images we have only go back to about 2016 or 2017. So it's a much shorter time over which it's happening. It's something that I think would be really cool to look at a much higher temporal frequency, because Landsat's approximately every 16 days, versus Planet Labs can be almost daily, though out here on the atolls, we're closer to about every 2 weeks, I'd say. So that would be really cool, is to think about, well, what temporal changes do we see with these high spatial resolutions on the much more frequent repeated satellite images? And that's something that we're kind of starting to get into. We're also looking at using AI to do a different way of automatically classifying the images. So right now, as I said, we only classify them into land, water, and reef flat. And part of that is driven by the fact that with Landsat, we can't really easily resolve too many other land cover classifications. We run into issues just because, if we try to say classify infrastructure, on a lot of these, MOTUs, that might be only 1 or 2 pixels, or it's usually sub-pixel level. Versus if you're using Planet Lab, then we could start to have significantly kind of more variation in what we classify. So great question. Thank you.
I also started using Planet in my research as well. So I'm glad that other people are finding a lot of usage out of the new availability of using the satellites on Planet.
Yeah, it's great. It's just the matter that the problem with these locations is, the lagoon could be huge, right? But the islands only occupy a total of like 10 square kilometers. But the coverage that you have to download from Planet Labs is, say, 100 square kilometers. So I'm paying for a lot of extra space that I don't really need, which is why we use the free limits, which I'm really happy they have, and it's a great resource.
Ismar says, thank you for answering your question. I have a couple more. If Facebook Live would like to leave any more, you can also do so as well. So as I mentioned earlier, since I'm a bit new to the geoscience space, you talked a lot about like sea level rise and that affecting the atolls. I was wondering, a lot of the climate change concerns are also focused on like the temperature of the ocean and like ocean alkalinity. So I was wondering if you could talk about how they might also be affected by things like ocean alkalinity.
So kind of tropical islands, and atolls in particular, are listed by the UN and the IPCC as kind of highly vulnerable, very high risk to a myriad different impacts of climate change. Okay. So I tend to focus on sea level rise because that's something that is somewhat easy to model, frankly, and has just been focused in the past. But exactly as you're saying, issues with ocean acidification and ocean temperature can have really big impacts on the coral communities. And a lot of the work that's been done with atolls has been very bio-focused and looking at kind of the survivability of these reefs. And the key aspect for me with that is really thinking about the fact that these little islands are made up of pieces of coral. So if we kill the reefs, we're turning off the sediment supply potentially. It's not the only sediment supply. There's also usually sediment supplied by kind of algae growing, other kind of microorganisms, etc. But typically things that are affecting the coral are also going to be affecting a lot of those other sediment supplies. So that is a major concern, no question. And it's one of the reasons why kind of thinking about these fluxes and how that might be changing is key to considering how these islands are going to survive. But yeah, they're really under a lot of stress, right? Not just changing storms and frequencies, but also these other aspects of, overfishing, for example, or ocean acidification or warming temperatures. But the interesting thing is, if you look at what's been documented, these islands have survived rises in sea level in the past for some of them. They have actually seemed to have kept up so far with rates of sea level rise. There's large variation in kind of changes to spatial area, for example, of these islands over the past like 50 to 70 years. And so it can really vary, but so far they actually seem to be doing better than we might expect at first glance.
Okay, thank you so much. That was a really great explanation to my question. I do not see any more comments or questions. So I guess we can kind of close off this discussion. Thank you so much for your talk today, and I really personally enjoyed it. I hope that our viewers did as well.
Thank you. Thank you for inviting me. It's always fun to talk about this, so I appreciate the chance.
Thank you for all those who joined, especially on our Facebook Live, as well as Clara and Christy who joined on the Zoom call, both to monitor and also just to hear about your work. Right, and make sure to stay tuned in 2 weeks for our next GeoSeminars talk. And thank you all so much for coming and for a great speaker.
Hey.